If you've ever thought, what if an F1 car just kept accelerating? You're not alone. Formula 1 cars are already the fastest circuit racing machines on the planet, routinely hitting speeds that commercial airliners reach during takeoff. But what if we just kept going all the way to 1,000 kilometers per hour? That's 620 miles per hour for all of you watching in the USA. What would happen to the car? What would the driver experience? And what does physics tell us happens when we breach the boundaries these machines were designed for? Let's find out. At 100 kilometers per hour or 62 miles per hour, an F1 car is barely even trying. This is highway speed for regular cars, but for an F1 machine, it's merely the beginning of its operating range. F1 drivers hit 100 kilometers per hour before they've even crossed the intersection at pit lane exit. The tires are likely still below their optimal operating temperature, meaning they're not yet providing maximum grip. As we cross 150 kilometers per hour or 93 miles per hour, the aerodynamics of the F1 car start to show their brilliance. At this speed, an F1 car generates downforce roughly equal to its own weight, around 798 kg. This means the aerodynamic elements are pushing the car into the track with a force equivalent to the car's mass. Theoretically, at around this speed, an F1 car could drive upside down in a tunnel because the downforce would hold it to the ceiling. The engine is still operating comfortably, though fuel consumption is increasing as drag begins to build. The car's responsiveness is improving, responding to even the slightest steering inputs with immediate precision. For the driver, things are still well within their comfort zone. They're starting to feel some resistance when turning the steering wheel due to increased downforce on the front tires. As we push past 200 kilometers per hour, the F1 car truly comes into its element. Now, the downforce has doubled or more compared to what we had at 150 kilometers per hour. The aerodynamic surfaces are generating tremendous downward pressure, far exceeding the car's weight. The car feels like it's suction cupped to the track. At this speed, cornering forces in fast bends can subject the driver to around 3 to 4 G laterally, meaning they feel 3 to 4 times their body weight pushing them sideways. For context, most roller coasters max out at around 3 to 4 G, and only momentarily. The noise level in the cockpit is rising dramatically. The world outside is beginning to blur at the edges, as the driver's perception narrows to focus on what's ahead. At 200 kilometers per hour, the car is covering over 55 meters every second, almost the length of an Olympic swimming pool. Braking points and turns approach much faster, requiring heightened concentration. The car's ride height is pressed lower by the increasing downforce, which means any bumps in the track surface could send showers of sparks as the titanium skid plate underneath scrapes the ground, a spectacular visual effect often seen in night races. For the car itself, systems are starting to work harder. Cooling becomes more important as the engine revs climb. Aerodynamic drag is building exponentially as drag in general increases with the square of speed, so the engine is working against an increasingly resistant wall of air. Despite this, the F1 car is still well within its performance envelope. This is a speed commonly maintained through high-speed corners at circuits like Silverstone or Suzuka. At around 300 kilometers per hour, 168 miles, we're experiencing what F1 cars routinely hit on the long straights at circuits like Monza or Baku, where modern cars can exceed 330 kilometers per hour. The forces at play are now enormous. The aerodynamic downforce might be 3 to 4 times the car's weight, meaning each tire is being pressed into the asphalt with thousands of kilograms of load. At approximately 360 kilometers per hour, an F1 tire experiences up to 1,000 kg of load and spins nearly 50 times per second. The contact patch deforms under this massive strain, while the top of the tire fights huge centrifugal forces trying to tear it apart. The driver is now experiencing the full intensity of F1 racing. They're pulling around 5 G under braking, 5 times their body weight pressing them forward against their harness. During quick direction changes, they feel 4 to 6 G of lateral force. Their helmet, now weighing several times its normal weight due to these forces, requires immense neck strength to control. Breathing becomes more deliberate and controlled. The driver's heart rate likely exceeds 170 beats per minute, not primarily from physical exertion, but from the combination of adrenaline, G-forces compressing their organs, and the intense concentration required to control the car at these speeds. The world outside the cockpit is rushing by at over 83 meters per second. That's a football field from goal line to goal line, excluding end zones. This information is strictly for the USA viewers who are still measuring stuff in feet and raccoons per bottle. When are you switching to a good enough metric system, by the way? Let's just give up on this one. The driver must look far ahead, anticipating rather than reacting, as human reaction time becomes a limiting factor at these velocities. The engine is reaching its maximum power band, likely approaching 12,000 RPM or higher. The transmission is managing enormous torque loads, shifting gears in milliseconds. Every component in the powertrain is being stressed. Despite this, 300 plus kilometers per hour is still within the design parameters of a Formula One car. The highest speed recorded in an official F1 session is about 378 kilometers per hour, set by Valtteri Bottas in Baku, aided by a slipstream and DRS. We're approaching that record as our speed continues to climb, but what happens when we push beyond the envelope of normal F1 operations? What occurs when we aim for 400 kilometers per hour and beyond? I'll tell you one thing for sure, things get really interesting real quick, so keep watching. Pushing past 400 kilometers per hour, 248 miles, takes our F1 car into the realm of the unknown. No Formula One car in a race has ever reached this speed. It's well above the typical gearing and power limits of even the most advanced Grand Prix machines. At this velocity, we've left the comfort zone of conventional F1 engineering far behind. The car is screaming through the air, covering more than 111 meters every single second, nearly the length of a football field. The slightest disruption in aerodynamics could spell disaster. This speed barrier isn't theoretical. Engineers once pursued a project specifically to break 400 kilometers per hour using an F1 car. In 2006, Honda took a modified bar F1 car to the Bonneville Salt Flats and eventually clocked a two-way average of 397.3 kilometers per hour. To reach such speeds, the Honda team had to make special adaptations to the car. The rear wing was completely removed and replaced with a stabilizing fin to maintain straight-line stability. The car ran a minimal downforce setup to reduce drag, and the engine was specially tuned to run at full throttle for extended periods, something F1 engines aren't normally designed to do. Aerodynamically, at 400 kilometers per hour, stability becomes a life or death concern. The F1 car's standard wings that provide beneficial downforce at normal racing speeds now produce so much drag that they'd prevent reaching such velocity. But simply removing them creates another problem. The car could potentially flip over. During the Bonneville project, engineers discovered that without some front wing, the nose could start to generate lift like an aircraft, risking a catastrophic flip. They had to retain a small wing profile to keep the front end planted while minimizing drag. The tires, which were standard F1 rubber in the Bonneville run, had to be inflated to double their normal pressure. This reduced rolling resistance and heat buildup, but sacrificed grip. Not a problem on the straight salt flats, but potentially deadly on any kind of circuit. At approximately 400 kilometers per hour, every component is pushed to its limit. The suspension risks bottoming out from extreme downforce, and the air itself becomes a formidable barrier, slamming into the car with immense pressure. At these speeds, human reaction time becomes woefully inadequate. If something goes wrong, it's likely too late to correct it by the time the driver perceives the problem. However, I'm finding it woefully inadequate that I'm using such big words and still didn't get to 10,000 subscribers. So, don't forget to subscribe. What's particularly striking about reaching 400 kilometers per hour is how the relationship between power and speed has changed. To go from 300 kilometers per hour to 400 kilometers per hour doesn't require 33% more power. It requires roughly double the horsepower because aerodynamic drag increases with velocity. The 400 kilometers per hour barrier represents a significant milestone. It's the point where an F1 car stops being a pure racing machine and starts becoming something closer to a land speed record vehicle. The compromises required to reach this speed would render the car unsuitable for an actual Grand Prix circuit. But what would it take to break 500 kilometers per hour? 500 kilometers per hour, or 310 in miles, is a speed only reached by specialized vehicles like top-fueled dragsters, not circuit racers. If an F1 car kept accelerating toward 500 kilometers per hour, several critical systems would likely fail before reaching this mark. In practice, even the best F1 tires probably wouldn't survive sustained use much beyond 400 kilometers per hour. Land speed record cars like Thrust SSC had to use solid aluminum wheels because any rubber tire would rip itself to pieces, and explode at those speeds. The physics is unforgiving. At approximately 500 kilometers per hour, a wheel would be spinning so fast that the outer edge experiences centrifugal acceleration on the order of thousands of Gs, far beyond what any rubber compound can endure. The engine power required to push through the wall of drag at 500 kilometers per hour is enormous. By 500 kilometers per hour, the drag is so high that an F1 car's 1,000 horsepower engine would be woefully insufficient. For context, top fuel dragsters that are the kings of straight line acceleration produce over 11,000 horsepower and can reach about 530 kilometers per hour in just 3.7 seconds. Aerodynamically, at 500 kilometers per hour, the vehicle would likely need a completely different shape. The exposed wheels of an F1 car create around 75% of the drag at high speeds, acting like 4 parachutes. To go faster, you'd have to cover or remove them, which essentially means it wouldn't be an F1 car anymore. The human body inside the cockpit faces challenges just as extreme as the mechanical components. At 500 kilometers per hour, the forces acting on the driver would mimic those experienced by fighter pilots pulling maneuvers in combat, but instead of lasting for brief moments, these forces would persist. Blood circulation would be significantly affected, with fluid shifting toward the lower extremities. This isn't racing anymore. This is survival. Pushing toward 1,000 kilometers per hour, 621 raccoons per bottle, on land is so extreme that only jet-and-jet rocket cars have ever attempted it. This is almost Mach 1, which is approximately 1,235 kilometers per hour. I'm not doing it in miles again, sorry, run out of jokes. No conventional car, certainly no F1 car, could approach this without essentially becoming a different machine altogether. As a vehicle nears the speed of sound, the air in front of it can't get out of the way fast enough. Shock waves begin to form. These are sudden changes in air pressure that occur when you compress air faster than it can disperse. The stability becomes extremely tenuous. The Bloodhound engineers from a more recent land speed record project had to simulate how shock waves from the nose and wheels would interact and even reflect off the ground back onto the car. The ground effect adds another wrinkle. A shockwave can't propagate into the ground, so it bounces, and you get a complex air pressure pattern between the car and Earth. This was something never encountered in F1 or any normal racing. It's pure rocket science. At Mach 1, air temperature in the shockwave can soar. Parts of the vehicle could heat up to a few hundred degrees. A tiny pebble or debris hitting the car at these speeds is like a bullet impact. An F1 car is not built for that. We've seen such things happen in F1 races before. When a spring from one car hit Felipe Massa's helmet in 2009 at perhaps 250 kilometers per hour, that nearly cost him his life. That's why every time I watch a race and there is tons of trash on the circuit, like Las Vegas for example, I get worried. It doesn't take much to keep one street clean for a few hours, does it?
The truck hits like Mario Kart. There's like plastic bags everywhere.
At 1,000 kilometers per hour, the vehicle covers 277 meters every second. Human reaction time, which is typically 0.2 to 0.3 seconds, means the driver would travel 55 to 83 meters before even responding to a hazard. So, is there a hard speed limit on land? In theory, as long as you add more thrust and make the vehicle more like a rocket, you could approach orbital velocity. But the atmosphere will always win eventually. By around Mach 5 to 10, you're basically dealing with re-entry physics. The air becomes an incandescent plasma around the vehicle, and clearly no car could survive that. Practically, the limit for a wheeled vehicle is likely around Mach 1 to 1.3. Beyond that, stability and tireless wheel technology become near impossible. Is it cheating to use airplane technology to break land speed records? Well, that's exactly what Thrust Team did. Thrust SSE was a technological marvel, far removed from conventional automobiles or even racing cars. Designed by Richard Noble and his team, it was powered by 2 Rolls-Royce Spey turbofan engines, the same type used in the F4 Phantom II fighter jet. Together, these engines produced over 100,000 horsepower, roughly 100 times that of a Formula One car. The vehicle itself was massive, weighing 10 tons and measuring 16.5 meters long. Rather than rubber tires, Thrust SSC ran on solid aluminum wheels that wouldn't disintegrate at supersonic speeds. Its unique aerodynamic design was crucial for maintaining stability while breaking the sound barrier, a challenge never before overcome by a land vehicle. On that historic day, in October 1997, thrust SSC rocketed across the desert floor. It created visible shockwaves in the dust and produced a sonic boom that echoed across the landscape, tangible proof that the sound barrier had been broken. This event secured current land speed record that stands at 763 miles per hour, 1,227 kilometers per hour, set by Thrust supersonic car on October 15, 1997. Driven by RAF fighter pilot Andy Green at Black Rock Desert in Nevada, this day marked the first time a land vehicle officially broke the sound barrier. Following the success of Thrust SSE, many wondered what the next milestone would be. The answer came in the form of the Bloodhound project, an initiative announced in 2008 with the ambitious goal of reaching 1,000 miles per hour on land. The Bloodhound supersonic car, later renamed Bloodhound LSR, represented the next evolution in land speed technology. The vehicle was designed to use a combination of a Rolls-Royce EJ200 jet engine from a Eurofighter Typhoon and a hybrid rocket, generating a combined 135,000 horsepower. The project made significant progress, with the car completing test runs in South Africa in 2019, reaching speeds of 628 miles per hour, using only its jet engine without the rocket booster. These tests proved the viability of the design and suggested that the 1,000 miles per hour goal might be achievable once the rocket system was installed. However, the Bloodhound project has faced numerous challenges, primarily financial. The team filed bankruptcy in 2018, was temporarily saved by businessman Ian Warhurst, but then faced renewed financial difficulties. In 2022, Warhurst announced he was stepping away from the project and wanted to sell the car, stating, "I've not got the choice but to let somebody else have a go at it. I can't put my hand in my pocket and pull out another $8 million. Which is fair, neither can I." With the Bloodhound project stalled and no other serious contenders currently visible, the question arises, will Andy Green's 1997 record ever be broken? History suggests that the record will eventually fall. Throughout the 20th century, periods of stagnation in the land speed record were always followed by technological breakthroughs that enabled new achievements. The current 27-year standstill is unprecedented in modern times, but may simply represent just a longer cycle of development. One thing for sure though, it won't be done with an F1 car.
Verstappen is out of qualifying and in Q1 for the first time in his career.
Up to around 300 kilometers per hour, an F1 car is in its natural habitat, a precision instrument performing exactly as designed with the driver and machine working in harmony. Between 300 to 400 kilometers per hour, we enter a transitional zone where an F1 car can still function, but requires significant modifications and begins operating at the edge of its design envelope. Beyond 400 kilometers per hour, an F1 car essentially stops being an F1 car. It requires such extensive redesign that it becomes a specialized land speed vehicle that merely resembles its racing origins. So next time you're looking at Lance Stroll spinning into the barriers, ask yourselves, do you have the balls to go that fast? And by the way, how fast was your fastest drive? Like for real, incriminate yourselves in the comments and don't forget to subscribe.